Hey students, welcome back. This is Unit 2, Molecular and Ionic Compound Structure and Properties. This first part should be review for you, so hopefully it'll go fairly quickly. Our homework today is a review of naming, not so much over what the notes that we're doing, but yeah, so we're going to jump right in. This is 2.1. We're going to start with types of chemical bonds. So first off, we need to figure out what a chemical bond is. A bond is when an atom shares electrons, or it could be transferring electrons completely. So what we have here is a picture of energy bond formation. And what we have, this first one is hydrogen. So we've got hydrogen here. And if the nuclei are too close, they're going to not be very attracted to each other because the protons or the positives are going to be too close, and so there's going to be some repulsion there, so they will go apart. So our optimum distance apart for hydrogen atoms is 75 picometers. All right. Then as they move further apart, there's going to be less attraction as they move further apart, and then when they get so far apart, there's going to be no attraction because they are so far apart. It's like they're lost in the mix, if you will. Okay, so think about that, and also remember to look at this right here. We have some overlapping of our electron clouds to create those bonds. All right, so as a quick review, hopefully we've got our type of bonds, our types of chemical bonds. Our first type of bond is our ionic bond. This is between a metal and a non-metal. This is where our electrons are completely transferred. So we have charged particles here. So we're talking about charged particles. Holy smokes, my writing is really rough when it's that small. Okay, so we're going to say charged particles here. All right, we have ions, thus the name, all right, ionic. Okay. Then we have our covalent bonds. This is a bond between two nonmetals. This is where our electrons are shared. All right, so our electrons are shared. Obviously, our covalent bonds are actually not quite as strong as our ionic bonds, and we'll get into that a little bit later. And lastly, you may or may not have heard of metallic bonding in your last chemistry class, but metallic bonding is where our electrons are pooled together. And we'll talk about those a little bit later in this unit, but for right now, this is just kind of an overview. So jumping into the reasons we have bonds and what type of bonds we have is based on electronegativity. And electronegativity is an atom's attraction for an electron. And this is within a bond. So we've already got a bond going. And so how much does that atom attract electrons to itself? Okay, so let's first get our trends out of the way. Our trend is that it increases across the periodic table. So as we go to the right, it increases, our electronegativity increases. Why is that? And that is because we have the same, we're talking about the same row, right? All right, so we have the same layer of electrons, and so we're adding more protons. More protons will pull the electrons tighter or attract the electrons. Also, the same kind of goes up as we move up towards fluorine on the periodic table. The electronegativity increases as well, and that is again due to less shielding. All right, we have less shielding, less layers of electrons to kind of get mixed up with, so we have less shielding going on there, thus creating fluorine being our most electronegative element, and francium is our least electronegative element. Francium is number 87 on the periodic table. All right, our noble gases, not involved in this at all. So group 18, not a part of electronegativity because they do not attract electrons to themselves. All right, so here's a good question for us. The electronegativity of oxygen is 3.5. So oxygen is 3.5, and the electronegativity of chlorine is 3.0. So both are the same distance from fluorine. They're both one step away. So explain why oxygen is so much higher than chlorine. And the reason I do say so much higher is because fluorine is 4.0. That's the max. Our electronegativity is on a scale of 4. Okay? Kind of odd, but we'll not talk about that right now. All right. So why do you think oxygen is 3.5 and chlorine is 3.0? What is the major factor taking place there? Right? Hopefully you guessed shielding. There is less shielding in oxygen so we have greater attraction there. So shielding kind of is the bigger point, right? Whether we have more protons or shielding, shielding takes precedence. So the less electrons that we have. Now, what this electronegativity all leads to is like when we look at two atoms, their difference in electronegativities when we subtract them, like let's say we have oxygen and fluorine bonded, their difference is 0.5. We take 4 minus 3.5. All right. So when they have a small difference in electronegativities, we consider that a nonpolar covalent bond. And what that means in nonpolar is our electrons are shared equally, and we'll see it in that picture down below. But the one thing they want you to remember in AP chemistry is that CH is considered a nonpolar covalent bond. And that actually makes sense when we talk a little bit more about organic, or maybe in your biology class you've talked about the organic portion. All right. Then in the middle, we have a difference of 0.4 to 2.0. We call these polar covalent bonds. These are where the electrons are not shared equally, and we're going to see that in a picture below. But an example of that is HCl. Then we have a large difference, and that's where the electrons are completely transferred, such as NaCl. So if we look at this little picture below, right, we'll get back to dipole moment, but we're going to look at the picture below. So see how chlorine, they're sharing equally, so there's not an electron density around it. Then if we look at the polar covalent bond, we have H, which is not very electronegative, and we have chlorine, which is very electronegative. So the electrons are spending more time at the chlorine atom, creating this slight negative charge. Thus it's polar, right? It's polar, just like this side is slightly positive. Right? And that actually changes the properties of a compound if it's polar or nonpolar. All right? Then we have an ionic bond, and that's where the electrons are completely transferred, but still have some of that kind of pole situation created there. So let's go back up and revisit dipole moment. Dipole moment is just a fancy way of measuring the polarity. All right? Measuring how polar a substance is. All right, the key here is that a lot of people get confused and they think it's a moment in time. It is not. It's actually a measurement of how polar a substance is. Okay, so now let's roll on to percent ionic character. Percent ionic character is just a way of measuring how ionic a bond is, and every bond has some amount of ionic character. All right, so measuring, and we could even say how the electrons are interacting or how the electrons are being shared. All right, let's say transferred, since we're talking about ionic, right? Okay, so we're talking about how the electrons are being transferred. And what you can see is we have a graph that's percent ionic character. As we get more and more ionic, like LiF seems like a very ionic compound, right? Which makes sense because they're so far apart on the periodic table. Look at their difference in electronegativities. It's like 3. That's a pretty large difference, okay? Whereas if we look over here, like HCl, right? Its electronegativity difference is 1, so it doesn't have as much ionic character. All right, but it still has some, so that's something we need to look forward to. All right, hope that helps. See you next time.